my name is Kate Larson. I have been a faculty member here since 2004, so it's my 11th year. And I do artificial intelligence. Now, artificial intelligence is a really, really broad topic area. And I would argue it's the most exciting part of computer science, particularly today. The changes which are going on right now are almost inconceivable from when I started my graduate work. So it's just been an amazing revolution. Now, my particular area of research is in what's called multi-agent systems. In particular, I'm interested in how multiple agents, programs, computers, people interact in different ways. So I spend some of my time thinking about how to design good markets or auctions. We spend some of our time thinking about how voting might work when there's computational issues arise, as well as how do you design systems so that the different components all sort of cooperate and work nicely together. And so then when I was asked, though, to give a talk to you guys today, I thought that instead of talking about some sort of highly theoretical work, which I find really, really exciting, but might be a little bit more esoteric to a general audience, instead I would talk about sort of AI in general. So in particular, I have two goals for today. I'm going to start off and just take like the first 10 minutes and talk about some of the really cool stuff which is happening in AI right now. Because as I said, it's just it's blowing my mind. And then the second thing, sort of the technical talk, is that I will hopefully walk you through a particular machine learning algorithm called ID-free, or an extension of C4.5. And what I hope to do, and we'll see how I work, is that we'll go through step by step how it works. Hopefully we'll do an example on the board, so by the end of today, you would all be able to go off and write this up by yourself. And why I chose this algorithm is that it's one of the most popular, widely used machine learning algorithms today. Okay? They come every now and then, people will generate lists of most influential algorithms, and ID-free and C4.5 tend to be sort of the top of the list. Okay. So what we're going to do, we're going to start off with a quiz. So I'm going to need you guys to answer. In particular, I have a list of tasks. Try to get an idea as to what computers can do today. Okay. So does anyone think computers can play soccer? Mixed feelings about that. What about play a decent game of Jeopardy? Yeah, go Watson, right? Okay. Drive along a curving mountain road. Okay, some support for that. Drive safely along King Street in Waterloo. Okay, again, sort of mixed. Buy a week's worth of groceries on the internet. You know what? Some people are mixed. What about go to the grocery store for us and buy a week's worth of groceries there? Okay. Discover and prove a new mathematical theorem. Converse successfully with another person for 1 hour. Perform surgical operations. What about put away the dishes and fold the laundry? A robot butler. Can we do that today? Sort of mixed support there. Translate spoken Chinese into spoken English in real time. Okay. Write a news story that will be published in the newspaper. Write an intentionally funny story. Okay. So I have some people who are real optimists, and I have some people who are really cynical as to what computers can do today. So let's see what we can do. Okay, hopefully the colors are not working well. So I have green, yellow, and red. It's a little bit unclear how well it shows up. And tells you, sort of green is, yes, we absolutely can do this today. Yellow is kind of, with a few caveats, and red is we're not there yet. So play soccer, absolutely. There's a robotic league called RoboCup, which they're adorable. And they play soccer with each other. Okay? And there's been huge been a lot of progress here, in probably about the last 15 years. When I started doing my PhD, I went to a graduate school called Carnegie Mellon University, which has a massive AI program, and there's a lot of roboticists. And they played a lot of robotic soccer. And it was at the situation where the players, they were little Sony Aibo dogs at the time, they were not particularly good. You know, they'd fall over, and then they'd take a lot of time to get themselves back up, and they weren't really cooperating very well. Now they're playing kind of soccer that you actually would like to watch with humanoid robots, and it's really quite exciting. They aren't at the point where they could take on a human team, okay, for a whole bunch of reasons. They're not as fast, they're kind of heavy, you wouldn't want to have a robot fall on top of you. But the goal, the grand vision, is that by 2050, a robot team would be able to take on a World Cup, so a soccer team. Okay? So we're on the path. A lot of people seem to have heard of IBM Watson's Jeopardy winning program. So yeah, so absolutely computers can do that. Drive along a curving mountain road completely autonomously? Yes. And they've been able, autonomous vehicles have been able to navigate situations like that for quite some time now. Okay? Drive safely along King Street in Waterloo. This is an interesting one. I have it in yellow. There are autonomous vehicles. They are driving on our streets. I think starting in January, Ontario is actually going to have a pilot program where autonomous vehicles are going to be on our roads. But it's driving along kind of in start and stop traffic where there's construction and there's pedestrians crossing at different places is a pretty hard task. So I'm going to say it's caveats. We'll see how this goes. Buy a week's worth of groceries on the internet? Yes, absolutely no problem. Right? You don't even need, they're sort of talking about technology now where you might have some sort of sensors in your fridge that will be able to send a message to your artificial intelligence about that you've run out of milk, and your AI will be able to order milk from the store. Doing something like that is actually really easy. Okay? Buying a week's worth of groceries at the grocery store is a much harder task, and we're not there yet. Well, what would make it hard? Well, you'd have to have a robot, some physical entity to actually go and do the groceries. It would have to be able to find the grocery store. That's easy. But it would have to also be able to navigate the grocery store, figure out where everything is on all the shelves, figure out what you need, and so on. So again, we're not quite there, but we're getting there. Discover and prove a new mathematical theorem. Computer programs can definitely prove mathematical theorems. There are some very famous theorems that have been proved by computers, and quite a long time ago. Computers are also in sort of computational creativity. There are people out there who are trying to create computers or programs that can go and discover sort of new mathematical facts. Okay, so they can do that. What they have found so far, that a lot of the things that the computers will discover tend to be things that maybe we already know. So it's a little bit unclear whether they can discover something new. But they're getting there. Okay, they will be able to, I'm positive they will be able to do so. Right now, it's a little bit unclear if they're creative enough at this stage, like today. I have conversed successfully with another person for 1 hour. I should have put a few caveats there, because the computer can definitely, little chatbots can sit there and talk back and forth forever. Whether they can fool somebody cause somebody to think that they are a person as opposed to a computer for an hour, we aren't there yet. That would involve passing what's called the Turing test, which is a very famous test that we talk a lot about in AI, where the idea that we want to be able to get a computer to fool a person into thinking that the computer is a person. They run Turing test competitions every year, and I think they have had some programs which are extraordinarily good. They can carry on sort of conversations with people and usually fool people, like a lot of people, for 10 minutes or so. But after a while, or people who are aware that the possibility of talking with a computer can often sort of figure out that something's a little bit off. Performing a surgical operation, there were some people who were kind of leery about this idea. I heard some like, oh no, we'll all die. There are probably some aspects of some surgeries which could be automated, but right now we still rely on surgeons. That is not to say that artificial intelligence is being used heavily in the medical domain. And I'll sort of give an example on the next slide, which I think is really cool, sort of more closely related to my own area of research. But we're not letting the robots operate quite yet. There's the case of putting away our robot butler, so putting away the dishes and doing the laundry. Okay, what do people think about that? I forget. There was some excitement. I'm not. Okay, I have small children, so I would love something like this. I'm going to show you a video in the next slide or two, so next few minutes, where a robot actually is folding laundry. Real-time spoken translation between languages, that has been done and it's been deployed. So it's entirely possible. You cannot see what's going on in the other room, but it's entirely possible that in the other room there is I'm giving the lecture in French or Mandarin or whatever. We can do that. I had write an intentionally funny story. Again, we're not quite there yet. Computers can certainly write funny stories, but whether they intend it to be funny or not is a question of debate. But writing a news story, yes, computers are actually writing news stories. These news stories are appearing in the newspapers. However, again, there are some caveats. Currently, the news stories that computers write tend to be on sort of sports or business, but not necessarily sort of larger human interest situations. So if any of you in this class had ever had any dreams of being a sports journalist or a business journalist, then I might reconsider, because the computers are taking over there. Okay. So let me just take a drink. Okay. So again, here's some pictures. So what can a computer do today? We already talked about autonomous vehicles. So I'm sure a lot of you have heard of Google's autonomous fleet of cars. So that top cute little car right there is an example of what I think Google has on its campus. And they drive around sort of the Google campus in California, taking people where you want. On the other side, the car right next to it is actually a Tesla, which you can go and buy today if you have enough money. And I was looking at the specs. I forget the name of the program, but basically they have a cruise control program, which is now in all their S series. It's an example of S series. And if you read it very carefully, it's an autonomous vehicle. They have this big caveat. You have to keep your hands on the steering wheel. However, once you turn on the software, the car will, by itself, set the speed limit. It will change lanes. It will navigate you to where you're going, and it will parallel park for you. Okay? And that's on the roads now. If you have $100,000, it could be yours. I was really tempted. Okay. Right? And so I would argue that these vehicles are on our streets. Okay. What in the middle here, what you have, this is actually an app. I believe it's a Google app. And it does our automatic translating. I don't remember what the app is called, but it's just showing examples. So I see a sign, I guess, in Russian, and you show the picture, and it will take the text, and it will convert it into a language of your choice. And this is done in real time. That's pretty easy. On the bottom, in the middle, we have two of the little robots that are playing soccer against each other. Okay, they have a little ball. They're just absolutely adorable. Right here below, they have a picture of a robot. It's actually folding laundry. And what I'm going to do is I'm going to show you a quick video if it's going to work. So just to sort of illustrate that we can actually have a computer which will do household chores. Now let's see if I can, see. I think I had the settings. Now I've sped it up a little bit because it takes a long time. This is a robot that's coming from, they're in Berkeley. Now, in their video, they have sped it up significantly, and then I have additionally sped it up because I did not say that we have robots that can do laundry quickly. Okay. Okay. There, that's done. Yeah, I think a round of applause for the robot. Whoopsie, I do not want. Another one coming. Can they only fold towels? I don't know. I don't know. However, it was folding towels and face cloths. Okay, right, okay. It's really hard. My guess that it probably can. I didn't watch enough videos. I didn't read enough of their papers over the weekend to figure out exactly what clothes that they can fold or not. But those were towels it had never seen before, and you think, oh, well, how hard is it a towel? What the robot has to do, it has to recognize that it has a towel, and all towels are different material, they're different sizes, they're different colors. So that's pretty tricky itself. It has to figure out kind of where the ends are to straighten up everything. Again, all towels can be all different sizes, so that cannot be pre-programmed. It has to manipulate things in real time. It then has to figure out how to straighten everything up and make it fold it so it looks really pretty, all without dropping it, and then it was stacking them really nicely. So all that is actually really hard to do, because it's done completely autonomously. Okay, there is no human intervention going on there. Okay. Again, some other examples. I have a healthcare example right there. It's a bunch of surgeons in the operating room. So I said that we do not have programs doing, or robots, for example, doing the surgeries or complicated surgeries right now. However, there's an awful lot of AI applications in the medical domain. For example, we talked very quickly about, everyone seemed to know who IBM's Watson was. It had won Jeopardy. Okay, but that's really fun, but now the thing is, well, what can we do that's going to be really useful to the world? And so one of the things that IBM's Watson is working on is going through sort of medical literature and trying to sort of synthesize sort of all this vast knowledge we have from all this research and try to come up with sort of interesting conclusions. Another example, which is a little bit more closely related to my own area of research, has to do with kidneys. In particular, if people have kidney disease, then usually the only thing that can be done is that they need a new kidney. Okay? And so so people need a kidney transplant. And there are different ways of getting a kidney. You can have it from somebody who has just died, who's donated the organs, or what's happening more and more is that someone can donate a kidney for you, because the person, you only need one kidney and you have two, you have a spare. Okay? And so the complicated thing is that you just cannot I can just not give my kidney to anybody. Okay? They have to match. And so unfortunately what sometimes will happen is that, so a parent will want to give their child a kidney, but there's just no match. They just do not match and not compatible. And so what we try to do is then sort of switch kidneys around so that a good match can be found. So maybe I'll donate my kidney, and then to somebody else who will donate their kidney to somebody else, and so we get this big ring. Okay. And what they're doing is that they're running AI-based algorithms in order to figure out how to do these matches and schedule these operations. Okay, and this is a deployed application that runs in the US. I'm not sure if it's running in Canada, but in the US they are running sort of these algorithms to figure out who's going to donate which kidney to who, and then also take into account sort of all the scheduling of the operating rooms and all the surgical teams that have to be in place. Okay. Another deployed application, again, this is sort of from my own research area, not a problem that I've worked on myself, but from my broader subfield, is illustrated in this bottom picture. That is actually a small picture from Los Angeles International Airport, and it's the police department that runs inside LAX. And how they schedule their patrolling strategy is actually based on an AI algorithm. Okay? They run something called a Bayesian Stackelberg game, and they come up with the patrolling strategies that way. The artificial intelligence ideas that have been deployed in LAX for quite a long time now is also used by the US Marshals for scheduling guards on the planes, used by the American Coast Guard to patrol some of the ports. I think Boston, for example, is one of the ports where it's been deployed. And they're also now expanding these ideas, and they're using them in other countries to patrol game reserves in Africa in order to protect animals against poachers. Okay? The ideas are all coming from the AI community. Now, my final example at the very, very top is breakthroughs. Anyone like old computer games? No, I'm going to date myself. I used to love Breakthrough. It's an old Atari game. So in AI, we actually spend a lot of time working on problems which are games. For a long time, people were really excited by checkers, and now checkers is solved. And then they were really excited by chess, and now chess for a computer is sort of not even interesting. Now people are pretty excited by poker, except that now the poker algorithms are pretty good, and the world champion poker playing humans can beat them, but I would never, myself, would never gamble against a computer. One of the more exciting things that have happened just in the last couple of years, actually this was from 2013, has to do with machine learning. And particularly by using a technique that they call deep learning, they were able to give the computer basically no information. All they did is they said, okay, here's a computer game, it's Breakthrough, but they've showed that it works on a whole bunch of different settings. And they say, your goal is to maximize your score, and all I'm going to give you is pictures. In particular, I'll show, you'll know what the screen looks like. You have the pixel information, maximize the score, and that's it. It doesn't tell anything about the goal of the game. It doesn't tell the computer about what the rules are. It doesn't tell the computer what the possible actions are. It just says, go off and figure it out. It took about an hour before I think my times are right, about an hour before the computer could play like a decent game of Breakthrough, and I believe it was within like 3 hours. It was just better than any human had ever been when it comes to playing Breakthrough. Okay? And they've been able to, and that's like 3 hours of practice from nothing, knowing absolutely nothing. The computer can teach itself how to play a game such as that. And they've been able to show that it works in all different sorts of games, and the idea that this can now be brought to other domains, and that now we have the capabilities where the computer doesn't need to know anything at all and just teaches itself from scratch. Okay? Which is just amazing. This was a dream for a long time and was unheard of even 7 years ago. And we can now do this. Okay. I had sort of mentioned earlier about journalism and how if you want to be a business journalism or a sports journalism, you maybe should rethink. I just grabbed this, this short story from a local newspaper. Just last week. So it says, Toronto Dominion Bank posts fourth quarter profits for $1.38 billion. It's by AP Press, blah, blah, blah. If you read it, it's not particularly exciting news, but it's reasonably well written. What's interesting is that if you look at the very bottom, it tells you who wrote it. This story was generated by Automated Insights. Right? So this is all completely computerized. There are other programs. Narrative Science is another company which does this for Forbes and also a lot of sports stories. And as long as you have some numbers, they'll go off and they'll write you a story. Okay? And this is just appearing in the newspapers. I also just give you an idea of some of the excitement that in the world about AI is that on Friday I just went to an AI curated news aggregator and just pulled off some random, the top headlines related to AI just for a single day. And these were them. And so it kind of gives you an idea of sort of the breadth which is being looked at in AI. So AI called them to tackle large hadron collider data deluge. The first computer-generated musical is going to debut. Someone's taught a computer to write like Engadget. One's going to rate your therapist, and so on and so forth. I think that inside the hacker, the world's first AI-designed car. We'll see how that goes. So on. But it kind of gives you an idea of the breadth. So this is just a news article sort of around the world for like the last day, and that was only sort of the top few that I pulled off. I think what's also, so this is a new thing. What else can computers do today? Well, they can even question our commands. See if I can get the volume to work. This will work if I have volume, so I'm not too sure. I don't want to, okay. Okay. So hopefully they're going to have the subtitles on. Okay, so the COMEX is the person says, stand up, the robot's going okay. Sorry, I don't have the volume because the voices of the robot's adorable. Okay, it says walk forward, the person. And the robot thinks about it. It says, I can't do this. So I have to do it again, and the robot says, no. The person says, I'll catch you. So cute, so trusting. And you would never, ever let your robot fall. Okay. So that's the example that's from Tufts University, human-robot interaction group. Sort of very recent results from the last few weeks. So that's really cool. Suddenly you have an autonomous machine, a robot, who will now question whether you're giving them good orders. Okay? So where does this lead us to? Well, as an AI researcher, of course, one of my favorite movies is 2001: Space Odyssey, and so, we're suddenly at the point where we have, I'm sorry, Dave, I'm afraid I can't do that. Right. So why might we want to have computer programs, computers, or robots that will now question our motives? Well, it's sort of for ethical reasons, right? The robots want to protect themselves, they don't want to put themselves into danger, but maybe now we have a situation where if somebody with nefarious intent gets access to a robot, the robot may put the brakes on something and say, no, I cannot do that. Okay. And that raises a lot of ethical issues inside AI. So we spend quite a bit of time, particularly in the last few years, really worrying about where this technology is taking us. And there have been people like Stephen Hawking who have come out just like sort of last year and said, no, we should put a stop on this. The computers are getting too powerful, right? And this is a concern, and there is sort of a very active debate going on right now, which people should be aware of. Unfortunately, I am running a little bit late on time, so I can talk about sort of ethics of AI and also sort of cool stuff that's going on in robotics forever. However, I am going to now change topics a little bit, and we're going to go through an actual algorithm that we use in AI. It's one of the most popular machine learning algorithms that we have. Okay. So one big thing in AI we want to do is that we want our computers to make decisions for us. Okay? So, for example, we might show it a picture like the top of that animal and say, what is this? Is this a panda or is this a bear? Or is this a panda or is it a dog? And we want our computer to tell us. We might have a lot of financial data, for example, credit card transactions. So we want the computer to say, yeah, that transaction is fine. Oh, no, this looks weird. This is fraudulent. Send a warning. Right? And then you get a phone call or an email from your bank. We might have some program which is taking in handwritten documents. The postal system tends to use this. You have all these addresses which are handwritten. They run it through computers, and the computers are recognized or what those numbers are, what those digits are, and forward things on appropriately. The trick is that people have different handwriting, and so who knows what people have written down. Or if you have email, you have a spam filter, and so there's an algorithm behind it which is sorting out your spam. Looking at reading your email for you and say, oh, yeah, this is a good email, I'll forward it on, I'll let you read it, and no, this is spam, I'm just going to file it away. Okay? So how in the world do we actually have a computer do that for us? Okay, they have to learn. We teach them. They get taught. And so the type of learning that which is often used, there are lots of different styles of learning, but this is a very popular one, is called supervised learning. And what you do is that you give your computer a bunch of examples which already have some sort of label attached. Okay? So in particular, so sort of I'll give an example, a less formal example, but what you have some data. It has each data point has a bunch of features or attributes, and then it has a classification. Okay? And so what we'd like to do, and there's something underlying the data which is providing this classification, these y values, but we don't know what that is. It's some function f, and we have no idea what it is. And we'd like to figure out what it is. We'd like our computer to sort of use all this data and say, oh, here's what the pattern is. Okay? So to make it a little bit more concrete, you can imagine what we have. We have our little computer in the middle, and we want our computer to learn different animals. And so we could provide it with pictures. We say, oh, that top thing, and it's a really cute picture, okay? And it's a bear. The next thing we have some pictures of some dogs, and we have a teacher there just saying, oh, here's a picture and here's a dog, some more bears, a sloth. And then eventually our computer will say, okay, I've got it, I've figured this out, and now we can feed it an example it's never seen before and ask it, what is it? And hopefully it will return the right answer. Okay. And this is a really common task. Okay. This is sort of, there's tons and tons of situations where we have some data, we have some labels on the data, and what we would like to do is to have our computer figure out how to do these classifications for us. Okay? And there's tons of learning algorithms out there for doing this. So decision trees, regression, neural networks, support vector machines, so on and so on and so forth. And so what we're going to talk about today is decision trees. Okay? Hopefully I have a few minutes. So we first have to look at our data that we would be providing our program. So remember, for a computer, what we're always doing is that we're always sort of mapping everything down into numbers. And so what our data would look like is that we'd have these examples, and each example would have what are called a number of attributes or features, okay, which are sort of different values, or just sort of points that the example can take on. So here I have a situation where I'm trying to figure out whether to play, I'm going to enjoy my favorite sport, and I know what the sky's like, I know what the temperature's like, I know how humid it is, and so on and so forth. So all those are going to be the attributes, and then I'm going to have, this is going to be labeled data, and so for each of my examples, it's going to be a set of attributes. I'm going to have that, yes, this was an example where I enjoyed my favorite sport, or no, it wasn't. And then from that information, I'm going to generate what's called a decision tree. Okay? It's like magic, but hopefully not by the end of, within the next 15 minutes, I'll tell you how this would happen. And once I have a decision tree, I will use that to do all the classifications in the future. So what I would do, I'd have some structure like this, and this actually provides enough information to make a decision for me. And so, for example, I might say, oh, today it's a sunny day, it's a hot day, has high humidity and strong winds. Computer, what should I do? Am I going to enjoy my sport or not? The computer's not necessarily ever seen this example, but instead we'll look at this structure that it's created, and it will say, oh, okay, well, it's sunny. So I see that top node, it's sunny, so I go down to the humidity node. The humidity node, we have high humidity, so then I go down, I follow the high edge, and I come up with a classification, and it says no. The computer would return no, saying, no, today I don't recommend that you play your favorite sport. Not today you're going to enjoy it. Okay. So this is what we're going to create. We're going to start from the data. We're going to create a structure like this. We'll then go off into the real world, and all our decisions will be made by this structure. The question is, how do we do it, and how do we know we have good trees? Okay. So what I've done is that I've just took my data set, my 4 examples with their labels, and I have created sort of 3 different possible trees. And we can ask the question, well, which is a good tree or not? Okay. If you look very carefully, and I'm not going to trace through it because I'm running a little bit short on time, we'll see the first tree is actually a really bad tree because it doesn't actually correspond with my data set in the first place. What I have in my data set are labeled examples, so we assume that these are true. So I don't like my sport when it's sunny, warm, wind humidity high, the wind's strong, the water's cool, the forecast is the same. But all the other cases that we've seen, I like the sport. If you run the examples through my tree, you'll see that things are misclassified. So this is not a good tree. The other 2 trees are good trees in that they are consistent with my original data. However, one's really complicated and one's really straightforward. Okay. Does anyone think which would be the better tree? It's going to be the smaller tree. This really complicated tree is sort of too complicated. It's found all sorts of patterns in my data, and I don't even have that many examples. So why would it return something so complicated? So by taking something that we call Occam's razor, which simply says if you have 2 explanations and one's easier than the other, you go with the easy one, we would say that this tree over there, the very small tree, is a pretty good decision tree. It's consistent with our data. It's not too complicated. So what we're going to want to be able to do is to learn those trees from our data. Okay, yeah, I should just. What I have here is the pseudocode for the decision tree learning algorithm. We'll talk about it really quickly, and then we'll go on to an example. Okay, I believe this is going to be online, so those of you who want to look at the slides later will have that available to you. The algorithm is quite simple, but it is using a number of standard computer science ideas. In particular, it's recursive, which means that it's going to be calling itself and working with smaller and smaller sets of examples. The first 3 lines are our base cases, which sort of tell us kind of what, it's a small thing we should do. If we don't have any examples, we're going to just return some value, which we'll predefine. If all the examples that we have the same classification, then we return that classification. If we have no more attributes or features are empty, then, well, we do a vote. Okay, that's not so important. Then we get down to the core part of the algorithm. At each step, we're going to choose some attribute. Okay? We're then going to create a tree. In particular, the tree we'll start off by having this one node. This is corresponding to the attribute that we've just chosen. And then we're going to sort our examples into different cases, depending on the value that example's attribute that we've just chosen has, because these attributes can have different values. And then we're just going to sort our examples into smaller sets that all have the same attribute value. And then we're going to call the decision tree learning algorithm again with these smaller sets of examples. And we're going to keep on, we're going to do this recursively. We're going to build up a tree, and then at the end, we're going to have a tree, and it'll be good. So I've done that really quickly, but what we can do, if I have a few minutes, is that we'll actually work an example. Okay. What I have is just some data, so I have 12 data points. And the example domain is whether I want to wait at a restaurant for a table or not. The attributes, so the labels are the target wait time, so do I wait or not? The attributes are, is there an alternative restaurant? Is there a bar at the restaurant? Is it Friday night? How hungry am I? How many people are there already? What's the price? Is it what type of food it is? How long is it to wait? And so on. Okay. Now, what we're going to do is that I'm going to start to work through how the algorithm would work. We might not have enough time to build up an entire tree, but we'll just sort of get started. So the first thing that we would do is that we would feed all of our examples into the algorithm. And we have lots of examples. They all have different classifications, so none of our base cases work. So the next thing we're going to do is we're going to have to choose an attribute. Okay? I haven't told you how to do that, but I am going to start by choosing the attribute for us just to get us started. And I'm going to say that patrons is a good attribute. So this is now going to become a node, the top node in my tree. And then the patron attribute, that column, has 3 values. It can either be full, there can be some, or it can be empty, or none, I guess. Okay? And so now what we do is that we sort our examples based on those values. So we go through and we say, okay, let's look at that first node. The first example, it had some. So we'll just put that example 1 goes right here. These are just sort of my notes. Example 2 was full, so we'll put 2 over here. And so on and so forth. So 3 was some. Say 4 is full. Let's see, hard for me to sort of trace this far. We have 4, 5 was full, 4, 5, 9, 10, and 12. 5, 9, 10, and 12. For some, you're going to have to read this off. That was 1, 3, 6, 8. 1, 3, 6, 8. So 1, 3, 6, 8. And then empty, or none, was, we go through, I see 7 and 11. Okay, so I've taken my set of examples. I've now sorted them based on the attribute value. And now I look at the classifications. In particular, I'll start at the empty, so 7 and 11. So 7 was F, so it means we do not wait. 11 was also we don't wait. So what I do here is I stop. So false. So I do not wait if the thing is empty. For some, I also look at the things. So I have some is I wait, 3 is I wait, 6 and 8, 6 and 8, I weight. So all these examples have the same classification. So that's going to be true. I then look at full, and if I look at my full examples, what I'm going to have is that some I'm going to weight and some I'm not going to weight. So I cannot come up with a classification right now. Instead, what I would do is that I would call my decision tree algorithm again, but applied only to this small set of algorithms. This is going to be the recursive call, sorry, set of examples. This is a recursive call. And then I'm going to do the same thing, but using only this set of algorithms. So what I would do is I then choose a new attribute. Let's see, I don't know, maybe type. Actually, type's going to be just for time things. Let's do something a little bit easier, true, false. We'll do alternative. Okay, so either I have an alternative or I don't have an alternative. And then what I would do, I'd take this small set of examples and I'd sort them again based on that alternative. So in particular, example number 2, there was an alternative. So 2 would go over here. 4, there was an alternative. This might have been a bad classifier. 5, we had an alternative. Yep. Wait, 9. 9 to no alternative. 10 is an alternative, 12 is an alternative. So 9 goes over here, but 10 and 12 will go over here. Again, I have a simple example on here where there's no alternative. That is where number 9, so the classification for this branch is going to be that I do not weight, so false. Over here, if you look carefully at the data, I'm going to have sort of mixed, they're going to have mixed values, mixed labels. So I would then recurse, but using only this small data set right here, and continue on. I choose a new attribute, I'd sort these examples based on that attribute's values, and keep on going. Okay. So the hard bit, that's how the algorithm works. This is, again, one of the most powerful machine learning algorithms that we have. It's very widely used. The trick is choosing the attribute. Okay, that's where the really interesting question is here. Because some attributes are going to be better than others. So I chose in my example when I began working this sort of the patrons as a good attribute. And certainly it's much better than choosing type as an attribute. And if you look at this picture, you kind of get some intuition as to why. In particular, with patrons, what it allows us to do, it sorts out our examples so that we're pretty good at, we've already been able to sort of end our tree. We come up with classifications pretty early. We have none, we actually have we already know how to classify that. For all the examples, some have the same classification. We only now have to sort of continue on working on the examples where there was a lot of people in the restaurant. If we chose type instead, just the way that it splits up our data, we're no further. What we had originally, that half our examples were positive examples and half were negative examples, we've divided up all of our examples. We've done quite a bit of work, but now in each case, we still don't know how to classify because we have an equal number of positive and negative examples. So that would be a bad attribute. And there is sort of a mathematical formalism of this notion as to why some attributes are good or not. And in particular, the way the algorithm works is that you're choosing the attribute that maximizes the expected reduction in entropy. And there's a math where entropy is sort of a notion for measuring how random a particular random variable is. And so there's a mathematical formulation for doing this. Okay? So if we ran this is the decision tree that we would actually end up. And so what we could do, that we can now take this and determine what we should do for when we're at a restaurant. Do we wait or not? And it's not particularly complicated. We had 12 data examples. We end up with a relatively small tree. It only we'll use testing 4 different attributes. It's coming up with a classification at that point. It's consistent with the data that we've had. So all our data examples will run through it and come up with the correct classification. And it's not too complicated. So this is probably something that we could then use, be comfortable taking out and using in the real world in situations that we have never encountered before. Okay. Again, one last thing I just want to point out. So we say how well is our algorithm doing? Our learning algorithm will do a good job, be a good learning algorithm, if it comes up with a classifier, so this decision tree, which does well on examples that we've never seen before, okay? So which are not labeled. So how in the world do we figure out whether it's doing well on examples that it's never seen before? Well, we often do a little bit of engineering, and we hold back some of our data and we create a test set. So these are examples where we have the label, but we never let our algorithm actually look at. So and we see how well it performs there. And what we tend to see, this is actually for the restaurant domain. We see that as our training set size gets bigger and bigger, the more examples that we see, then our test performance, so how good it is at predicting unseen examples, the classification of unseen examples, tends to improve. And in this particular example, we're getting, the accuracy is about 95%. So it's getting examples that it has never ever seen before correct, probably about 95%. So it could work really, really well. And in particular with these trees, the more examples that it sees before you do this test, usually the better that it's doing. Okay. And unfortunately, I'm out of time. But that was a really quick explanation of an algorithm called ID-free and how it works. It sort of goes through the data, it chooses attributes, it reorganizes the examples based on these sorts of examples based on the attributes, and eventually works down until it gets classifications. Okay? And as I said earlier, ID-free and an extension called C4.5 are, these are used all over the place. They tend to be, if you have a supervised learning task, so a situation where you have some data with interesting attributes or features and then a label associated with it, often ID-free or C4.5 is one of the first learning algorithms that you're going to try to apply there. Okay? And you now have the pseudocode. You should be able to go off and program this by yourself. And then the final thing I just wanted to say is that right now AI, the stuff that we're being able to do in artificial intelligence is sort of mind-blowing. I've been doing this involved in AI starting grad school about 15 years ago, and the stuff that we're able to do now was we didn't even conceive that it would be possible in that time frame. And particularly the last couple of years, the progress has just been amazing. So I hope you consider AI in the future, and thank you very much.